Good? Yeah, sounds good. Right. Okay, so welcome back from the break. We're going to talk a little bit more about, well, laser science, but in particular about massive black holes and massive black hole binaries in this lecture. But before starting, um, so I was pointed out yesterday that, of course, I have to say my fair amount of bullshit. Can I say bullshit? Yeah. In my lecture. So when we talked about the verification binaries yesterday, I messed up a couple of systems. So I essentially messed up HMCNC with ANCVN, right? So this was the system I was talking about for which we know essentially everything. And instead, in fact, it has a very small error bar. This system doesn't have an error bar because we don't know what it is, essentially. So it's just, which is, I mean, they could have been a bit more like, but anyway. So that just to point out that the system we're referring to is AMCVN, is not HM Cancri. Okay, so having said that, can start. Yeah, second lecture we talk about supermassive black holes. Okay, and supermassive black hole binaries or massive black hole binaries. I mean, there's really no difference between the two. Sometimes we refer to them as supermassive, sometimes as massive. I mean, they're massive in general. Right. So first of all, well, we can start with some. So this is a why I have this thing in here. I don't know exactly. No. Okay. Well, this is just I think it's a map of the galaxy distribution in the universe from probably SDSS, right? So we are in the middle here, and so you see essentially this is every dot here is a galaxy, and this is just increasing in redshift. This is just from up to redshift 0.5 or something. But you see that, of course, the distribution of galaxies that we have in the universe is definitely not uniform. It's definitely clustered. There are nice, cluster here in the center, and there are filaments leading to these clusters. Okay, and one of the major challenges in astrophysics and cosmology is to actually understand how all of this comes about, right? Oh, there are some, well, this is nothing to do with the universe. I mean, this is just, bits of the sky that are missing. You see fringes here. They are because depending on the redshift, you might see or not see specific lines that you use to classify the redshift of a source. So there are definitely things that are not um, really cosmological here, but you get the idea of the structure, right? So well, we have a general picture for the understanding of the evolution of the universe. I don't know whether it is correct or not, but it's the standard model that we have for that. So essentially, we now think that we live in a so-called lambda CDM universe or something similar to it, where essentially the energy content of the universe is dominated by something that we have no idea about, which we call cosmological constant, or dark energy, or quintessence, or you can call it whatever you like. We have no idea what it is. So we have a much better idea of the remaining 30%, 27%, and this is matter. Fortunately, about 90% of it, we don't know what it is. And we call it dark matter, okay? Right, so we can go down, take out this 24%, we are left with 3%, 3-4% of the matter in the universe, and those are baryons. And those we know what they are, except for the fact that if you look at the universe and you count the baryons in galaxy, you're missing more or less 50% of them, and we don't know exactly where they are. Okay, so we have, let's say, we have a fair understanding of 1% of the universe, I would say. But anyway, the idea is, even then, the idea is pretty, well, simple in a sense. So you start off with something at the beginning of time that we call Big Bangs, followed by a period of inflation that leaves a sort of distribution of matter with some inhomogeneities. Okay, there is a field of perturbation that there are expanded by inflation, and at the end of inflation, you are left with this perturbation field in the matter density field, and this perturbation grow in time, and we will see a little bit about that in a second, and they start to form the first bound structures that there will be the nurse of the first proto-galaxies and then galaxies. And this is essentially the idea that we have, the general idea that we have about the evolution of the universe. So remember that when we talk about the universe, we talk usually, we express, well, really we express both time and distance with a single parameter, which is the redshift. You know, sometimes you use redshift to, you know, describe the distance of an object. Sometimes you use redshift to define, you know, how much was passed in time. The redshift is just, of course, the relation between the emitted frequency of a photon and the observed frequency, and is 1 plus z is proportional to the scale of the universe at a given redshift. Okay, so essentially the redshift gives you just the relation between the how big is the universe, you know, the scale of the universe today and the scale of the universe at that redshift. Okay, this is how much it expanded the universe in that time. So redshift 0, of course, is today. And you know, one thing that it's obvious, but people tend to forget, you know, also people working in this field tend to forget, is how nonlinear is the relation between redshift and time. Okay, the universe is 14 gigayears old. Okay, today we are at redshift 0. At redshift 1, we are already 80 gigayears ago. Okay, at redshift 6, we are about 13 gigayears ago. Okay, so between redshift 6 and redshift infinity, okay, there is only 1 gigayear. And between redshift 6 and now, there are 13 gigayears, okay? So this is important, especially when we talk about the formation of the first structure, the first black holes and stuff like that, because this usually happens at redshift around 20 to 10, which seems, you know, a long time, but, you know, between redshift 20 and 10, there is only about 100 million years. So everything happened very, you know, on cosmological scales, very quickly, okay, back in those days. Right. So let's start from some observational facts. So why we are interested in supermassive black holes? Well, we are interested in supermassive black holes because every time, you know, in every occasion we had enough sensitivity to actually resolve the nucleus of a galaxy, we found like a dark concentration of mass in it that for simplicity we will call massive black hole, okay? There is actually essentially, I mean, for the vast majority of these objects, there is no proof that they are black holes, okay? But, you know, it's the simplest interpretation that we have of them. Moreover, we see quasars shining at high redshift. So quasars are just point sources of energy, okay, like stars, but they are a spectrum that is very different than stars, okay? Stars emit like a black body, and quasars have a spectrum that extends from radio to gamma rays, okay? And they are point objects, and the interesting thing is that if you look at their spectra, you see that the redshift can be huge. Okay, we see quasars that are already at redshift 6. Now the record holder is redshift 7.5. Okay, now if you assume, if you think about it, you have a point source at redshift 7.5, and you know, despite of this, you see it. So it means that the luminosity of this source is ridiculously high. And the only, you know, foreseeable mechanism to produce this thing is accretion of matter into some compact object, but not a stellar mass black hole. You need a massive black hole, in this case of, you know, billion solar masses, okay? So we see black holes, let's say dormant massive black holes in galaxy today. We know that supermassive black hole power quasars at high redshifts. So we want to understand something about their formation and their evolution. And you know, we will see how this is relevant to gravitational wave astronomy and why gravitational wave astronomy is the, you know, is probably the key to unfold the evolution of these objects, okay? Right, so this is just a collection of pretty pictures just to point out that, okay, so this is like a superposition of two wavelength vision of a galaxy. So this is optical, you see a bulge of stars, and if you look in the radio image, you see these huge jets, okay, that are, you know, that resemble the jets that Samaya was showing later, but, you know, instead of being on AU scales, these are on hundreds of kiloparsec scales, okay, so they're pretty big. This is an FR2 galaxy, so this is again the core of a galaxy. There is an accreting object here, and you see these radio lobes. So these are pretty much a megaparsec across, okay? And you know, you can zoom in this galaxy, and you see that there is some luminous matter here going on, and there is something obscuring them. So this is what we call the obscuring torus that is surrounding this accreting black holes. So, as a matter of fact, we see we see these supermassive black holes. We see them eating a lot of stuff, right? So accreting mass, but we also see them ejecting a lot of stuff, right? And forming jets and stuff like that. So we can gain a lot of information about these objects by observing them in electromagnetic window. So one of the key problems with supermassive black holes, which I would say is unsolved, is where are they from? Okay, what are the where do they come from? Because certainly we don't have any model to form a billion solar mass black hole from scratch. Okay, you can't just take a giant ball of gas and just collapse it in a 10 to the 9 solar mass black hole. That doesn't work. Okay, there's too many other physical processes that happen, along the way that cause that thing to fragment and form stars and stuff like that, right? So, so let me just walk you through a little bit the story that I sketched at the beginning, and a little bit more details. Okay. So the universe, say after the, you can, if you want more details, you can take the Bible of dynamics, which is here, chapter 9, and you can learn all the details about it. So the universe after the Big Bang wasn't completely uniform, and you have this perturbation in the matter density field, right? But these perturbations are dominated by the dominant part of the matter content of the universe, which is dark matter. Okay. So what happens? Dark matter, you have this density fluctuation in dark matter, and of course, an overdensity starts to feel its own gravity, right? So you have to think about things are not collapsing. You have to think that you are in this expanding universe, expanding background, and your overdensity is expanding as well, but a little bit slower because of the self-gravity of the overdensity itself, right? At some point, what happens is that as the universe continues to expand, this overdensity reaches a critical point at which essentially it decouples from the Hubble flow, right? So essentially it reaches a maximum size, and then essentially the self-gravity of the object wins over the expansion, and the object turns over and starts to collapse, okay? And in collapsing, essentially you have a mechanism that is probably not very well understood, which is called, don't even remember the name, violent relaxation, okay? And you sort of virialize, and you form a virialized object with a given mass and a given size, okay? And this is what we call dark matter halo, okay? Of course, there is a whole theory about this that you can see in the aforementioned chapter of Binet Remain. So you can actually start from a Gaussian perturbation field, and you can actually work out what is the typical rate at which these objects collapse and how they build up in time. And what you find out is this process is hierarchical. Okay, so you collapse objects that are smaller and lighter first. Okay, so the first object that you can collapse are sort of mini halos of small mass, like 10 to the 5, 10 to the 6, so million solar masses. Now, of course, the actual minimum size of this halo depends a little bit of the nature of dark matter, etc., etc. So we're not concerned with this here. But the only thing important here is to understand that the small object light structures form first, and this is what is shown in this plot here. So here you have halo mass on the x-axis, and this is the number of halos per unit moving megaparsec, okay? So these are curves at different redshift, from redshift 20 to redshift 0. So I've taken redshift 20 here because we see that redshift 30 to 20 is where things start to become interesting. From the Big Bang up to redshift 30, nothing much really happens in terms of structure formation, okay? And we'll go in a reason for that in a second. So just to put some scale here, the Milky Way, so do you know how massive is the Milky Way? 10, 11. Okay, 10 to the 11 is right, but it's the mass of the stellar component, right? The mass of the dark matter halo of the Milky Way is more likely 10 to the 12, okay? So the typical galaxy like a Milky Way sits in a halo like this. And you see, for example, that there are essentially no halos like this at redshift 10, and they're very rare also at redshift 5, okay? 10 to the 15 is a typical dark matter halo that hosts a massive galaxy cluster, okay, just to put some scale. And 10 to the 9, 10 to the 10 are maybe typical halo of dwarf galaxies, okay? So just to put things into scale. So you see that, for example, halos that can host supermassive, very massive clusters as we see today, they start to appear in the universe only around redshift 2 to 1, okay? So this is because of this hierarchical build-up process. So essentially what happens, I mean, I show a merger tree later. So you have these small halos that come into being. They feel each other gravity and they merge together, forming more massive and massive halos. And this is what we call hierarchical clustering. Yes? This is from a semi-analytical model. Yeah. It's not a measure, but you can measure the dark matter with some assumption, of course, the dark matter mass function, and it matches quite well, of course, in the high mass range at low redshift here, because we don't have observation at very high redshift. So but this is from a semi-analytical model. Now, so why redshift 20, redshift 30 are interesting? So the thing is that the potential well is dominated by dark matter, right? And baryons are just 10% of this dark matter. And remember, at the beginning, after primordial nucleosynthesis, you just have essentially hydrogen and helium. And you have a small dark matter halo that creates a potential well. All that baryons do is just following the potential well of the dark matter halo and sitting into there. Okay. So at the beginning, you just form in this dark matter halo, and the baryons start to sit into these dark matter halos. To start to do something interesting, you need to be able to cool the baryons, right? Because differently than dark matter, baryons can cool. So dark matter halos simply virialize and they form some bound structure and they stay there, okay? But baryonic matter, let's say atomic hydrogen, can sit in the center of this dark matter halo, and if the virial temperature, which is the temperature given by the kinetic motion of these particles, which is ultimately connected with the depth of the potential well, okay? If this temperature is high enough, then you can excite collisionally the levels of the hydrogen atom, and this energy can be then emitted via photons, so you can cool down your baryons. Okay, so you can convert the kinetic energy of your baryons into radiation and cool them down. Okay. Now, the way you cool them down, it's heavily dependent on the abundance of H2, which is molecular hydrogen. And the reason is that, well, atomic hydrogen, you really need to rely on Lyman cooling. Okay, you'd have to excite from the ground state to the second level. And to do that, you can compute the difference in energy, which is between the first and the second is what, 10 point something electron volt. And this corresponds to a virial temperature of 10,000 Kelvin. Okay, so 10,000 Kelvin is the typical temperature at which you can cool atomic hydrogen. However, if you are molecular hydrogen, then you have also the vibration and rotation level of the hydrogen molecules. Okay, which are much lower, which have, the spacing which is between them is not of the order of tens of electron volt, but it's just a fraction of electron volts. Okay, so you can start cooling them already at thousands of Kelvin. And why this makes a difference? Well, this makes a difference because there is a very, straightforward relation between the virial temperature of a halo and its mass. So the mass is the temperature of a halo is proportional to the mass to the 2/3. Okay, so more massive halos, this is also intuitive, they have deeper potential well, they have higher virial temperatures. Okay, so what is the consequence? The consequence is that if you have molecular hydrogen, okay, then you can cool already at 10 to the 3 Kelvin, right? So you can cool baryons in halos that are very small because this is proportional to the mass to the 2/3, right? But if you don't have molecular hydrogen, you have to rely on atomic hydrogen cooling, then you need 10 to the 4 Kelvin, 2 10 to the 4 Kelvin to cool down, okay? So you need to have more massive halos, okay? And this makes the difference because the type of objects that you start, the type of objects that you end up with at the end depends on the mass of the halo you are in. So this sets also why we are talking about things from redshift 30 or 20 and so, because if you actually compute the mass function of these halos as they form following this density perturbation, you see that essentially you start forming, let's say, halo that are efficient for H2 cooling around 10 to the 5, 10 to the 6 solar masses, right, at redshift 25. So at higher redshift, you don't have halos that are this big. So what happens at higher redshift, you just have this halo forming and the baryon sitting in the center of this halo, okay? And they start to cool down and form structure around redshift 20, 25. If you have to rely on H cooling, then you need more massive halos, more of the order of 10 to the 8 solar masses, and you have to wait a little bit farther to redshift 15 to 10 to start to collapse, to form, you know, objects from the cooling of this gas. So what objects do you form? Well, this depends on the nature of your cooling process. So in case that you have H2, so what happens is that you have cooling at around 1000 Kelvin. It starts to happen at redshift 30 in dark matter halos of million solar masses. So this cooling is very slow. Okay, very slow. It means that there is, it is in fact subsonic. Okay, so being subsonic, okay, it means that if you have your cloud of gas, it starts cooling down, and the rate at which it cools, okay, it can be communicated across your cloud because let's say the motion caused by this cooling gas, okay, within the cloud is slower than the speed of sound within the cloud, right? So you can actually cool down your object adiabatically in one go. So the consequence is that there is no or little fragmentation of the cloud. And this is very different from what happens. So what I'm describing here is essentially a star-forming cloud, okay? But it's a star-forming cloud with only hydrogen and helium, okay? This is very different from what happens in star-forming clouds now, that they are metal-rich, so you can have a lot of efficient cooling because of metal line cooling, okay? And the cooling is much faster than the speed of sound within the cloud, so you have efficient fragmentation. And this is the reason why today you form low mass stars in clusters, essentially, okay? Or groups. Now, there is no fragmentation, so you can form a very massive star. So you have an halo of, a million solar mass of dark matter, you can form very massive stars of few thousand solar masses, okay? And these low massive stars, you can see what is the fate of these high mass stars. This is a plot from Megar and Vosley 2002, I think. I had the reference here. So you see that essentially if you start with an initial mass of about 2,000 solar mass, you end up with a black hole of several hundred solar masses. So if this route of producing a collapsed object is viable, then you can have in these mini halos a population of seed black holes of several hundred solar masses, which might be an ideal, candidate for being the seeds of the supermassive black hole that we see today. Now, if you don't have H2, you have to rely on hydrogen cooling. And this happens in more massive halos with a lot more mass. So here you have, well, I'm not really following what is written there, but the main idea here is that you have a much larger cloud of gas, and somehow you have a monolithic collapse into a compact object. So now, the details of how this happens are complicated, and in fact, there is essentially, one general model for the formation of these very massive stars and seed black holes from these very massive stars I talked about before. There are gazillions of models for the formation of these collapsed objects from direct collapse, and which to me is a hint that we don't understand really the physics very well. Okay, so ideas are, for example, you form a very massive disk. Okay, let's say a disk of 1 million solar masses. This disk is two-brane marginally stable, which means that forms bars, and these bars are very efficient in getting rid of the angular momentum and conveying material to the center. So you can accrete material onto the central core at this rate of, let's say, a solar mass per year, up to the point where you form a seed black hole that accretes severely super Eddington, and at the end of the process you have like a 100,000 solar mass black hole or so. So these mechanisms, have a lot of, they have one problem, which is the problem of angular momentum dissipation. So essentially, if you do the math, you have a massive disk of hundreds of parsec scale, and you have to form in the end a black hole of 10 to the 5 solar masses, and the size of the black hole is its Schwarzschild radius, right? So you need to get rid of that angular momentum. So this is the main challenge of this type of models. Anyway, we are not going to go into any details of this, but the point is that we have several scenarios. So I list the two leading one here, but there is at least a third one, but let's forget about that, to form black holes at fairly high redshift. Okay, so let's say you can form hundreds or thousands solar mass black hole at redshift 20 via this POP3 scenario. These very massive stars I described at the beginning, they're called population 3 stars or POP3 stars, and are the first population of stars that are formed in the universe. They are essentially metal-free. Okay, there's a bit of confusion there because the first population is called POP3, whereas the last is POP1, which is like the sun is a POP1 star. Okay, but anyway, or you can form this supermassive black hole via direct collapse. Okay, the seeds of the supermassive black hole, and here you can form like 10 to 100,000, let's say, solar mass black hole at a redshift 15 to 10. Okay, so this is just a small sketch to tell you that there is a lot of research in the field, and we have ideas and we have models that cannot be really tested yet because we don't have observations that pierce that deep and that faint into the early stage of the evolution of the universe. But we have an idea of physical models that can produce black holes of a reasonable, quite massive black holes already at high redshift. Okay. Now, what happens next? Well, hierarchical evolution happens, right? So in these mini halos at high redshift, there are these proto-galaxies that are in the process of being formed, and then these proto-galaxies, they, following the galaxy the halo merger, they merge together and they form bigger and bigger galaxies, right? And they also accrete material from streams in the intergalactic medium, etc. So you have this hierarchical build-up process that from your collection of proto-galaxies and intergalactic gas, etc., forms the big galaxies that we see today. Okay, so somehow in this process of galaxy formation and evolution, also the massive black holes are involved, and you might be able to form a supermassive black hole starting from the seeds that we just seen. You can form in these, let's say in the mini halos at high redshift. So these are just snapshots of a simulation that describe this process, right? So you see here at redshift 5, you see this is a massive dark matter halo. You see that usually these dark matter halos are fed through filaments, and the galaxies go along these filaments, and you form a bigger and bigger halo. And this is essentially what could be, for example, the dark matter halo hosting the Virgo cluster at redshift 0, essentially, right? Okay, so this is essentially how things proceed. Now, so we've seen that the hierarchical build-up of galaxies, the build-up of galaxies is hierarchical, and we know that there are massive black holes at the center of galaxies, right? And one thing that we know quite well is that these supermassive black holes correlate with the properties of the Ross galaxies. So the only real property of a supermassive, first of all, black holes are defined by two parameters, right? So we have mass and spin, essentially. Forget about charge. Spin is very high to measure. It's very hard to measure. So there are measurements, but some of them are controversial. There are a lot of big errors, etc. Masses can be measured in several different ways, and some of these measurements are actually quite reliable. So you can plot the mass of a black hole against, for example, this is the mass of the stellar bulge of the host galaxy, and this is supposed to be the velocity dispersion of the galaxy. And the velocity dispersion, 1/2 sigma square is equal to gm over r, is a measurement of the depth of the potential well of the galaxy. And you see that there are nice correlations between the two, okay? Not surprisingly, I would say more massive black holes reside in more massive galaxies, and there is also a very nice linear relation between the mass of the black hole and the fourth power of the velocity dispersion, okay? So these are clues that, galaxy formation proceed hierarchically. Black hole properties correlate with the properties of the host galaxy. So the main idea is that the formation of supermassive black holes is also hierarchical, right? So the main model is that you have some seed black hole in high redshift, seeded in high redshift protogalaxy, and following galaxy merger, the two black holes are brought to the center of the merger remnant, okay? Inflow of gas lights them up, and we see them as quasars, shining as quasars, so they accrete mass along the process, and they eventually merge, forming a single massive black hole. And as this process repeats along the cosmic history, you form the supermassive black holes that we see in galaxy today, okay? So the way the supermassive black hole grows is essentially, there are two ways to grow them, is gas accretion, okay, and merger with other supermassive black holes, mostly, okay? There might be different channels, but these are the two that, are mostly involved in this kind of process. Now, let's have a look at accretion. Accretion is, well, essentially the process of, eating gas from a black hole, okay? So, but you have to think that you have some gas that is sitting at, formally at infinity, and you have to bring it actually to the horizon of the supermassive black hole. So you have a huge delta E, right? Potential energy between infinity and the horizon of the black hole, right? This change in potential energy is what is converted into radiation, okay? So now suppose, and we will see that better in a second. So now suppose you have a certain flux of proton, right, with density rho, that has been accreting onto a black hole of mass m, okay? Now the accreting material emits a radiation with a luminosity L, and the luminosity L is, we will see in a second, is related to the amount of material that you accrete, to the rate of accretion, and a conversion factor, efficiency between accreted mass and luminosity. Now, this, let's take your proton, your accreted proton, right? You have a gravitational force, which is gm, well, with good approximation, forget about general relativistic correction, is gm, mass of the proton divided by r squared, right? Now, this accreted material is also, however, is also subject to a flux of radiation that is produced in the accretion process, right? So there is a force exerted by the radiation pressure onto these accreting protons. And this force, well, is equal to the, essentially, well, is the momentum of the photon is h nu, is the energy L, is h nu divided by c, that's the momentum of the photon. So the total luminosity divided by c is the total, energy of the photon, times the cross-section, which is the Thomson cross-section in this case, relativistic Thomson cross-section, divided by 4 pi r square, that is the, shell at distance r square where you are computing your force, right? So an interesting thing that you see is that, okay, well, if this term wins, you keep accreting material. If this term wins, okay, then your accretion flow is blown away by the radiation pressure, right? The interesting thing is that there is no distinction between two regimes depending on the distance to the black hole, because you see you have the same dependence of r. So r cancels out, okay? So whether you can accrete or not, it depends only on essentially the luminosity that you are emitting, okay? So you can equate these two things together, this cancel out, and what you get is that there is a limit to the luminosity, which is called the Eddington luminosity, because Sir Eddington was the first to perform this calculation, at least to record, that has this form here, okay? So you see there are a bunch of constant, and most importantly, this is proportional to the mass of the black hole, okay? So essentially what this tells you is that, of course, all of this is computed in spherical approximation, and we are using it to describe an accretion disk. So, just take it with a grain of salt, but orders of magnitude, it works. I mean, observationally, we see that it works. So essentially, a black hole can accrete at the maximum rate which is proportional to its own mass. Okay, so just to give you an idea, this Eddington luminosity is 10 to the 38 ergs for a solar mass black hole. Okay, and scales with the black hole mass. So a billion solar mass black hole will have a Eddington luminosity of about 10 to the 47 ergs per second. Just to give you a comparison, you know, the luminosity of the whole Milky Way is 3 orders of magnitude smaller. Okay, so quasars are, you know, are the, let's say, persistent, most luminous objects in the universe. Okay. Now, so this is just an image of a quasar at high redshift. Now you have a luminosity that comes from accreting some mass, right? So luminosity is a d in the t, right? The mass you accrete times c squared is an energy, so you can work out a typical timescale for this process. And this is just mc squared divided by the luminosity of Eddington, okay? And since the luminosity of Eddington is, the Eddington luminosity is, luminosity of Eddington sounds a little bit, Sir Eddington was very luminous. Eddington luminosity is proportional to mass. Mass cancels out, and this Eddington timescale does not depend on mass and is of the order of 0.4 gigayears. Okay? Now, the mass that you accrete in this time, okay, you can actually, you know, convert this, since L is essentially an efficiency factor m dot c square, right? Because the luminosity is essentially the m dot c square that you're converting from matter into radiation, right? You can work out what is the m dot of your black hole. And the m dot of your black hole is 1 minus epsilon, where epsilon is the efficiency to which you convert matter into radiation, times the m dot that you are accreting, right? But then you can cast these into the Eddington timescale, and this is, you know, there is a factor that depends on the efficiency of conversion into radiation times the black hole mass divided by the Eddington timescale. And this F Eddington is just the fraction of Eddington at which you are accreting. Okay, so this is an expression that relates the mass of the black hole, the m dot of the black hole, into the to its own mass. And you see that is m dot proportional to m, which means that the growth in mass of the black hole via, let's say, steady Eddington limited accretion is exponential. Okay, the solution of this differential equation is an exponential of this form here. Okay. No. That really depends on what is your, you know, what. I mean, all of this is just very ideal. You assume an F ed, and you can work out what is the accretion of the black hole mass, the growth of the black hole mass. But of course, F ed, it depends on, you know, the astrophysical processes that allow you to bring the mass close enough to the black hole to be accreted. So that's actually a problem. how you actually do that. So the problem with dark matter is that, okay, so the point is that to accrete this, I mean, yes, you can also, I mean, you don't have any Eddington limit for dark matter, right? Because it doesn't emit any radiation. The problem with dark matter is that it is essentially collisionless, right? So to accrete matter onto a massive black hole, you need to bring it there. So it needs to have low enough angular momentum, right? So somehow, one of the main problems in accreting the mass of the supermassive black hole is that we need to bring the gas close enough. And, you know, with gas it's not that hard because gas is dissipative, so you can easily, let's say, dissipate away the angular momentum and just, you know, through an accretion disk, you just make the gas accreting onto the black hole. But with dark matter, you know, it's very difficult. Either you have a dark matter particle that just, you know, intersects the black hole and just plunges into it. Otherwise, you know, it's not going to be accreted. And we know that in the core of galaxies, in the center of galaxies, the density of dark matter is actually orders of magnitude smaller than the density of stars and gas. So it's going to be a very subdominant effect in the growth of the supermassive black hole. Yeah, I mean, there are several maps of, dark matter halos for many clusters, and those are actually used as a benchmark for the numerical simulations that we have. So one of the main, one of the other interesting topics in galaxy formation is to reproduce the angular momentum distribution of galaxies, which is non-trivial. And we get some information from dark matter maps and galaxy maps, and we try to reproduce that with the numerical simulations. Yeah. Okay, just move on. Now, the important thing is that I just mentioned briefly is this efficiency factor here. Okay, what is the efficiency factor? Is the amount of energy, is the amount of mass that you radiate away in energy. Is the fraction of mass that you radiate away in energy. Well, what is the delta E that you need in order to accrete a material from infinity, to bring your particle from infinity to the horizon of the black, to the last stable orbit of the black hole, right? This is, well, infinity, the energy is 0, is minus gm, m is the mass of the black hole, small m is the mass of your accreted particle, divided by 2 times the radius of the inner rim of your accretion disk, right? So the luminosity is minus d in the t by definition, so it's gm m dot divided by 2 r rim, okay? What is r rim? Is the innermost stable orbit of your accretion disk, okay? And this depends on, and this, you can cast this, as a function of, you can write this as a function of the Schwarzschild radius of the black hole. Schwarzschild radius is 2gm over c squared. So if you do that and you just put a beta times the Schwarzschild radius of a black hole, you find that this luminosity is 1 over 4 beta m dot c squared. And this 1 over 4 beta is epsilon, okay? Now all of this is Newtonian, so you should apply a relativistic correction, but it's just to give you an idea. For a Schwarzschild black hole, okay, the last stable orbit is x6m, right? And beta is equal to 3. So this efficiency factor epsilon, when you apply a relativistic correction, etc., is of the order of 0.06. Okay, is actually less than 10%, right? But if you have a maximally spinning black hole and you're accreting on a prograde orbit, your innermost stable circular orbit is essentially, is essentially m. Okay, is gm over c squared. So this efficiency goes up to 0.42, right? Because you have you brought the black hole, the particle much closer to the black hole before being accreted, so you have emitted way more energy. Okay, so this is just to say that usually we say, well, efficient accretion converts 10% of the mass into energy, into radiation, but this is actually, there is a factor of 5 or more difference depending on the spin, and this is critical because this efficiency enters like this in computing the mass growth. So now you see what happens. You see that if you have a non-accreting black hole, a non-spinning black hole, this typical time scale of accretion is 30 million years. But if your black hole is maximally spinning, it becomes 300 million years. And this is the e-folding time of the mass of your black hole. Now, how old is the universe? It's 14 billion years, right? So, okay, 300 million years, 14 billion years, you have like, what, 50 e-fold times? 50 e-fold times is more than enough to accrete a black hole from 100 solar masses to 10 to the 9 solar masses. You need like 22 e-fold times to do that, e-fold in mass, okay? But at redshift 7, the universe is 400 million years old. So now you see where's the problem. The problem is that if your black holes are highly spinning, there's no way you can accrete mass, you can accrete a seed black hole of 10 to the 4 solar masses to billion solar masses within 300 million years. But if the spin is kept close to 0, then you can do it because your e-fold time is a tenfold smaller. Okay. The problem is that in general, accretion tends to spin up the holes. So there is a kind of, it is unclear whether and to what extent you can form the supermassive black hole that you see at high redshift via efficient accretion. Of course, there are routes. There are, way out of this. For example, if you have, instead of having coherent accretion, you have accretion from different directions. You keep the black hole spin low and you can grow it more efficiently. Or you can have supercritical accretion. So there is essentially no strong physical limit. The Eddington limit is not such a strong physical limitation to accretion. There are, in particular, when the supply of material is, so this is rather technical, but I just throw it there. When the supply of material is big enough, let's say your m dot is super Eddington, okay, you can puff up the disk becomes very dense, and let's say the time scale that you need to diffuse the photons out of the disk becomes smaller than the time scale for the material to be accreted. So your photons are affected in the accretion flow with the material, so your emission is suppressed. So if you have less emission, so it's not that efficient, you have less luminosity, so you can accrete more material and you can break the Eddington limit. And this is one of the ideas that people are now pursuing in order to form the supermassive black hole at high redshift. Did you have a question?
Yeah, I was going to ask about retrograde orbits.
Right, so that's exactly the idea, to keep the spin low. So if you have if instead of having accretion always into prograde orbit, or whatever is the direction of the angular momentum of your accretion flow, after some time, the black hole spin is going to align with that disk, right? So if you have a coherent accretion in a plane, even if the black hole spin has whatever random direction, it will eventually align with the accretion disk and you will have prograde accretion, okay? But if you accrete material in packets, okay, and these packets are either prograde and retrograde, then you don't have enough time to align the spin of the black hole with the spin of the disk. You can see accretion process like, you have a prograde accretion event, you have a retrograde accretion event. Now, the prograde innermost stable circular orbit is much smaller than the retrograde innermost stable circular orbit. So the amount of negative angular momentum that you transfer to the black hole for every retrograde accretion episode is bigger than the amount of positive angular momentum you transfer to the black hole to any prograde accretion event. So on average, you tend to spin down the black hole. That's why that's what is called technically chaotic accretion. That is why it's seen as a viable mechanism to grow quickly the black holes, because it keeps the spin of the black hole small. Okay. Yep. Well, you can see it. If you have between few hundred and few tens of thousands solar masses, there is a difference of 4 E-folds, right? 4 or 5 E-folds. So you see, it's like, you gain, in this case, you gain like 100 million years if you start from bigger. Oh, it's a joke, or we can barely come up with a mass, let alone with a spin. The spin of the initial seeds is, usually in all the models that I know, the initial spin of the black holes is either 0 or uniformly distributed between 0 and maximum. I don't think there is any way yet to predict what is the actual spin of these seed black holes. We have observation of black holes where we can infer the spin via measurement of the skewness of the K alpha emission line. And it appears, so those measurements have to be taken with a grain of salt. So it appears that black holes are in general quite highly spinning. But there is a significant trend with mass. Well, significant, I'm not sure. There is a trend with mass. So they tend to be highly spinning at the low mass end, and as you move toward more massive black holes, they are still significantly spinning, but the general trend is to spin down a little bit. And we can explain that with reasonable accretion models, connecting the geometry of the accretion to the morphology of the galaxy. If you look for my name 2014, there is a nice paper about that. Okay, so I'm at this point like an hour behind, but okay, let me just flash another this is very pedagogical. I think it's useful, right? Do you agree? You like it? Good. Right. So, we have evidence that the main mode of accretion of supermassive black hole, the main mode of growth of supermassive black hole is actually gas accretion. So what I said at the beginning, okay, you can grow mass via accretion or via mergers, right? But we have a key piece of evidence that at least, you know, at least most of the mass of today's mass of supermassive black hole got there via accretion, not via merger. And this is a very elegant and very beautiful argument, one of the most elegant arguments, in my opinion, in astronomy, astrophysics, which is the Salton argument that comes from Salton, who came up with it in 1982. So essentially, we have measurements of the luminosity function of quasars, right? So we can measure how many quasars are emitting at a given magnitude or a given luminosity. We can convert that, right, at any redshift, right? So of course, so we know the number density of quasars that are emitting at a given luminosity, okay, as a function of luminosity, right? So we can integrate this number density function over redshift, taking into account, of course, for the redshifting of photons, 4 pi over c, just a conversion factor, to get the energy density per megaparsec cube that has been emitted along the cosmic history via accretion from the luminosity function of quasars that you observe. Okay, so we can convert this luminosity function in the energy density that has been emitted via accretion along the cosmic history. But now we know that the energy density divided by c squared times this efficiency factor is the mass density that ended up into the black holes that accreted that mass, right? Is exactly what we're seeing here, right? Is exactly how m dot is related to the energy. So instead of having mass and energy, we have mass density and energy density here. So we have, we can measure this number here. We can measure that number. We can infer that number there, right? And if you do the exercise and you integrate the luminosity function of quasar, what you get is about 2 × 10⁵ solar masses per megaparsec cube. This is the mass density of supermassive black hole in the universe today that you would infer by converting the luminosity function of quasars into accreted mass. But we can measure the masses at the center of the black holes with different methods. So we can measure the mass function of these black holes independently on this argument. And what we get is something between 3 to 5, 10⁵ solar masses per megaparsec cube. So you see there is a factor of 2 difference. And the factor of 2 actually is nicely accounts for the fact that this calculation was done with the luminosity quasar, with the optical quasar luminosity function. And we know that about 50% of quasars is actually obscured in optical. You see them in X-ray, but you don't see them in optical. So you have to multiply this by a factor of 2, roughly. So you see that the amount of mass that you have built up through accretion along the cosmic history matches fairly well the mass density that we see today in supermassive black holes. That tells you that most of the mass of today's supermassive black hole, ended up there via accretion. Okay. Assume, yeah, there is actually you can use this argument to measure this efficiency, etc., etc. Now, I have to point out 2 things because these are really misleading. The fact that the majority of mass is gained through accretion doesn't mean that black holes don't merge. Okay, mergers inevitably happen, and we will see that in a second. Okay, they are just likely not the dominant accretion mode of black holes. First point. Second point, just to stress this, is that this is a order of magnitude argument. Even if 90% of the mass of the black holes is actually built up toward accretion, you can think with a scenario where you have a billion solar mass black hole. You accreted 90% of that mass toward through via accretion. So you take away 90%, you have 100 million solar mass black hole, and you still have room to build up that 100 million solar masses via merger only. And this is still consistent with the Salton argument, right? So this argument doesn't tell you in any manner that mergers do not happen or are not important in the growth of supermassive black holes. It just means that in general, the bulk of mass ends up there via accretion, okay? Yes? Oh, yeah, I mean, yeah. I mean, there is also a large dependency on this efficiency factor. Yeah. So it's actually I have to point out though that this problem is really not that severe as I stretch it here, because this is a very nonlinear function of the spin. Okay, if you have a spin at 0.998, this efficiency is 0.42. But if the spin is 0.95, it's already 0.16, 0.17. Okay, so the actual uncertainty that you have there, unless your black hole are really maximally spinning, but there are reasons to believe that this doesn't happen really in nature, or not very often, you have a factor of 2 uncertainty with this efficiency factor, more than a factor of 5. Okay, so let me just move toward the bulk of the lecture, which is, okay, well, we understood how they grow, but of course mergers happen, right? And we see galaxy merge in the universe all the time. Okay, this is an example of the mice. This is the the antenna, sorry. And these are the 2 cores of it's the zoom in this region, and you see a lot of blue stars, which means that there is a lot of star formation going on. There is this red core, means that there is a lot of dust in there, and these are the 2 nuclei that likely host 2 supermassive black holes at their center, right? And this is again you already seen something similar in this lecture. This is a sequence of a merger put together with 6 different pair of galaxies, obviously, right? So you see the 2 galaxies approaching each other. You have the first flyby. You create these tidal tails, then you come back together, and you eventually merge in a single object. Okay, and you can, this is the same kind of thing that you see in actually in simulations. Now, what happens to the supermassive black holes when 2 galaxies merge? Okay, so this evolution was first sketched by another paper that, if you want to read a beautiful piece of literature in astronomy that, was a field-defining paper for the next 40 years at least, because we still use it. Read this paper here. It's Begelman, Blanford, and Rees 1980. And each sentence of that paper triggered, tens of other studies in the literature. So when you study Begelman, Blanford, and Rees 1980, is a Nature letter. It's very short, beautifully written, and there is, whatever you study about supermassive black hole, there is a sentence that mentioned it in that paper. It's about supermassive black hole binaries. So what happens when 2 black holes merge? Okay, you have the 2 galaxies that come together, and the 2 black holes at the beginning are sort of the outskirts of the merger remnant, right? And what happens is that they actually fall toward the center because of dynamical friction. Okay, dynamical friction is just the collective effect of the interaction of the massive object with, let's say, the sea of stars that are surrounding it, right? So you have your sea of star, you have your massive object that is moving into this sea of stars. So you have like a gravitational interaction that deflects the mass of your test particle, let's say. And what happens really, technically, even though this I'm not sure is the correct picture, but what happens? So you have a black hole here. So you have your stars, right? And your black hole is moving into your sea of stars. The star is deflected, right? And what happens? You create a sort of big overdensity of stars because of this focusing effect. And the mass of this overdensity of stars is proportional to the mass of the black hole m, right? So what you have a breaking force that is proportional to m squared, essentially. So you can think of your black hole as, this is your galaxy. your black hole is here, is moving, let's say in circular orbit, right? It breaks down because of dynamical friction, and what it does, it just moves on to a more tighter and tighter orbit, and it spirals into the center. Okay, and this is because this funny property of gravity that has like negative heat capacity, right? So if you slow down, you go down on a tighter orbit, so you actually speed up, which is kind of interesting. So you see that you can actually, this force, you can work out the formulation assuming a typical Maxwellian distribution for the velocity of the particles, and you can actually see that this, in the limit of v, that the velocity of the black hole is 0 or much larger than the typical velocity of the star, this force goes to 0. And it's actually maximum, the drag, when the velocity of the black hole is of the order of the dispersion velocity of the stars. Okay, so if you have, for example, a black hole that moves with a circular velocity, which is usually of the order of sigma, in a sea of stars with a velocity dispersion sigma, okay, this is where you have the maximum effect of dynamical friction, and you bring the black hole to the center. Now, this works also with gas. It's a bit different. It depends on the density of gas and on the Mach number, but the scalings are exactly the same. Okay, so whether you have gas and stars, you actually bring the two black holes to the center because of dynamical friction. And these are simulations that show so. So this is an M-body simulation. So you have you are simulating interaction with stars, and you see dynamical friction bringing the two things together up to the softening limit of your simulation. And this is another simulation in gas, in a gaseous remnant, and you see the separation of the binary going down because of dynamical friction. Now, what happens then? Let me go back here. At some point, dynamical friction becomes inefficient. So it's not that if you have two black holes, you just can bring them together because of dynamical friction only. I mean, you bring them together, but you still have a long way to go. And the reason is the following. At some point, so dynamical friction acts on the black holes individually. At some point, what happens? The two black holes start to see each other, right? So their dynamics is not dictated anymore by their stellar and gaseous background, but by their companion. So they form like a bound Keplerian binary, right? And this bound Keplerian binary now responds to perturbation of the surrounding as a single object. So your encounters with the particles, with the sea of particles, do not act on the individual black hole just moving it to the center, but they act on the center of mass of the binary. This is just a perturbation to the center of mass of the binary. So when the black hole binary pairs, okay, dynamical friction ceases to be efficient. It's not efficient anymore. And this is a problem because usually for typical massive binaries, this happens, on a parsec scale. And if you compute the gravitational wave timescale, the merger timescale because of gravitational wave for a binary on a parsec scale, this is easily 10 orders of magnitude longer than the Hubble time, because the gravitational wave timescale is proportional to the separation to the 4th power. Okay, so you need to shrink the binary by 2-3 orders of magnitude in order to get down to a regime where the gravitational wave emission is efficient. So what you see here in this plot is in fact a cartoon showing separation in parsec here, and this is the typical timescale the binary spends at that separation. So you start off with dynamical friction that is very, very efficient up to the point you form a binary, and now you see that if you have dynamical friction only, then this goes asymptotically at infinity. And this is the age of the universe, so your binary just stalls, right? So you need to bridge this gap between parsec separation and sub-parsec separation. 3 orders of magnitude in binary shrinking somehow have to happen. And they could actually happen. That's what I'm gonna tell you in the next 10 minutes. And the first, so this is just the problem that I highlighted. The first mechanism, so we have to take into account that this binary is not isolated. It's still in a very dense environment. So now, the collective effect of your stellar distribution is not relevant for the evolution of the binary anymore. But interactions with individual stars is. And this is So now it's important to take into account for three-body interactions. So what happens is that you have a massive black hole binary, and you have a star that is on an orbit that is intersecting the binary semi-major axis. So you have a complex three-body interaction. The star, the system tends in some sense toward equipartition, which means that statistically you give energy to the incoming stars. The energy is ejected away with the energy, the star is ejected away with an energy which is much larger than the incoming energy, and that energy comes from the binary, so the binary shrinks. So if you can provide enough stars, if you can feed enough stars to the binary, you can shrink the orbit enough that you drive it to gravitational wave emission regime, okay? And I have some, that's the the typical energy. I have to speed up a little bit. That's the typical energy for an encounter. This is the number of encounter that you can consider having, a background of stars with a certain number density and a certain velocity dispersion. You can write down, equations for the evolution of the binary semi-major axis eccentricity and for the ejection mass. And in particular, I want to spend a second on this equation here. So this is the evolution of a semi-major axis of a binary that sits in a stellar density of, in a stellar distribution of density rho and typical velocity sigma. So you see that, and this h is an hardening rate. It's a dimensionless number, which is of the order of 15, okay? So you see that d in dt of 1 over a is essentially a number, okay? So the hardening timescale, the dA in dt is proportional to a square, which is what I'm going to show in the next slide. So you can think now of your binary, and you can write its evolution for interaction because of interaction within stars and gravitational wave emission. So you can write the total dA in dt as the dA in dt given by this three-body scattering plus the dA in dt given by gravitational wave radiation reaction. And as we saw, well, as you can see from here, if you expand this, the dA in dt because of three-body scattering goes with a square, minus a square, and the one because gravitational wave reaction goes with the a to the minus 3. Okay, that's the steep that we saw before. And the constant are these two numbers here. So now you see that, okay, you came up down here with dynamical friction, and now there is this scattering process that is efficient in shrinking the binary, but still its efficiency decreases as you shrink the binary. So it's something that ramps up like this, right? But at some point, you hit the point where gravitational wave emission becomes efficient, and you can actually merge. So the point is essentially where this intersection here is, right? And the typical timescale for coalescence is essentially the timescale at this intersection. So if you actually equate this dA in dt to this other dA in dt, you get the timescale for evolution of the binary, and that has this expression here. And for typical systems. For typical, well, I'm skipping a couple of things. For typical system, the transition radius is of the order of centiparsec, and it scales, almost linearly with the mass. This scaling with the mass depends on the density profile that you're assuming. And the typical time scale, if you take a characteristic density profile for a galaxy, let me just go here. The typical timescale over which this evolution happens can be actually up to several gigayears. Okay. So, and it's highly dependent on the density of the stellar background. So, hardening via interaction with the stellar background, okay, can actually bring the black hole binary to coalescence in timescale that are, from several hundred million years to gigayears. It really depends on the density of the stars, it depends on the mass of the black hole, it depends critically on the eccentricity of the binary. So you see here that if this is for different eccentricities, if the binary is very eccentric, your typical merger timescale decreases by almost 2 orders of magnitude. So if you can derive efficiently the eccentricity of a binary, you can actually make it merge quite quickly. Okay, So, but this is just to give you an idea of how you can overcome this problem that is called last parser problem, that you have a binary that you formed because of, the two black holes came together because of dynamical friction, but then, you need to get rid of the energy angular momentum, and interaction with stars can do that. Another way to do that is interaction with gas. And here, okay, if stars is actually relatively simple because it's just, Newtonian dynamics, there is just gravity involved. With gas, we talk about hydrodynamics, so it's way more complicated. And the only thing that I want to point out is a very simple idea. It's a very simple model to just give you an idea how this can work, right? So suppose you have a gaseous disk and a binary within it, okay? What happens is that the quadrupolar moment of the binary carves a gap in a hollow in the disk, okay? So now you have a disk that has a central rim, okay, where material tends to pile up because they find this quadrupolar forcing of the binary, okay? So now let's suppose for a moment that there are no streams here, and you just have this sort of dam, okay? So the material flows in, and then it encounters this forcing potential of the binary, and it just stops there, okay? So your particle that is moving around in this disk has an angular momentum, which is small m square root of gm over r, okay? So at this gap, what I call the gap radius, the angular momentum is m square root of gm over r, right? The evolution of the angular momentum within the disk, if the disk is fed with a certain m dot, which is constant in the disk, is dl in the t equal to minus m dot square root of gm over r, right? You have mass that is flowing at a rate m dot. This is the change in the angular momentum. I'm not addressing how this happens, right? Nobody knows really how angular momentum is transferred in accretion disks, okay? Just to be clear. Now, so this is the m dot, this is the L dot of the gas if there was no barrier. And since you are stopping the gas here, right, it means that you are injecting a dl in the t, which is the same and opposite, right? So the dl in the t of the binary, this is taken, of course, from the binary. So the dl in the t of the binary also has to be not equal, but equal, according to this, minus m dot square root of gm or gap, right? Now, assuming that the binary is circular, its angular momentum is the reduced mass times square root gm, the total mass times a. So you can actually compute what is the evolution of the binary by substituting by computing L dot and equating to this, and you find an equation for dA over A equal minus 2 square root of 2 dm over mu, which is the reduced mass. And this equation tells you right away that you essentially have 3 E-folds in accretion. You have 3 E-folds in separation by accreting a mass that is equal to the reduced mass of the binary, okay? So if you are able to feed to the disk to stop, an amount of mass that is of the order of the mass of the binary, you can efficiently shrink the binary because of this angular momentum transfer. Now, this is a very simple model. In reality, it doesn't really work like this because, this is not a perfect dam. You just don't stop material here. You create streams that are fed to the black hole and blah, 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 and all other stuff happens. But the main idea is that you can use this quadrupolar forcing to transfer angular momentum efficiently from the binary to the disk and shrink the binary, okay? And this process can also happen in tens of millions or hundreds of millions of years. So it might be another efficient way to overcome this last parsec problem. Now the third thing that you can do is to rely on triple interaction. So suppose that all of these mechanisms that I showed you before fail. Now you have a stalling binary, and this is I just put this in because Neil, which is gone, mentioned it in his lecture yesterday. So now suppose you have your massive binary that is sitting there, but the evolution timescale is several giga years, or a giga year even, and you are at very high redshift where things happen fairly quickly, there is a chance that a second merger happens that brings in a third massive black hole. And so you can form a black hole triplet. And actually, this is not, it cannot be very rare because, if you just take images of Sloan, for example, or Hubble, you see a plethora of multiple systems. You see merging binaries, merging triplets, merging quadruplets, okay, all sort of stuff. So you see that multiple mergers happen quite significantly in the universe, right? So you can think that, okay, you have a binary that is stalling there, a third black hole comes in, okay, and what happens? So this is something that we started to study. There is a lot of work in the literature about this, but we started to put this, it's gone here. We started to put this into cosmological constant contest with a student in Milan, Matteo Ponetti, and we developed a three-body code for evolving this binary, okay? So I actually brought the code with me. So we have a binary, right? So the start of, so I'm gonna do that's a real coding. I have to run the line. Right? So you have your binary, right? That is there sitting. Circular, it might be more eccentric or circular, but it's sitting there, right? It's not doing anything because it's stalling. Now you bring in a third black hole because of a subsequent merger. So what happens when you have a triplet? When you have, when you have a hierarchical triplet, what happens? No, I said hierarchical. Quasi-Lido resonances, right? So you have your binary that is still fairly circular, and you have a third black hole that comes closer, and you excite the eccentricity, and you have this quasi-circle. When you have a circular binary, a more eccentric binary, come back circular, go closer, you're going to eccentric. If you get eccentric enough, you can merge the binary, right? That's what you do. And that's the first simulation. And this is what you see here. So the third black hole is coming in. So these are the separation of the inner black hole and the separation of the outer binary with respect to the two central black hole. You see the outer binary is coming in. It excites the cycles, and at some point, the inner binary merges, right? However, you also know that things can be much more complicated than this, because, for example, if you arrive from a wrong angle, quasi resonances are not efficient. So your binary cannot merge. At this point, you have the third object that joins your system, and you have a complex three-body interaction, right? And at some point, you end up with a merger of the system, okay? That's not the only way it can happen, no? During the three-body interaction, you can also eject one of the systems. Good job, yeah, right? But actually, in many cases, okay, you lead to the merger of the binary, and this is what you see. This is what you see in the plot here, right? So you see three-body coming in, the third body coming in, exciting some quasi resonance, but it's still not efficient enough to merge a binary. And actually, if you see, like this is a zoom in of this point here. It's pretty bloody complicated what's happening there. So you have a lot of exchanging and stuff like that, right? And at the end of the day, during one of these chaotic interaction, you take the binary to coalescence, right? No, you have a two-body merger. You always have the third black hole sticks around or is being scattered away, etc. And then you remember at the merger, when you merge, what happens? Gravitational wave takes away mass. So you have a 5% mass loss of your binary, and you get a kick. Well, now, okay, so why I'm telling you all of this? Just, of course, to juggle the apples, first of all. But secondly, because this is important because mergers, three-body interaction, are actually a very important safety net for gravitational wave astronomy, especially for LISA and for supermassive black holes. In fact, one of the problems that you can always come up with is like, oh yeah, but you don't really know if the binary merge, etc. So what happens if they stall? Then we spend 3 billion euros and we don't see anything, blah blah blah. So here is a plot that we did essentially this experiment. We put this three-body interaction into a cosmological model, right? And what you find in the end of the day, we sample the parameter space, etc. What you find is that this three-body interaction can lead to coalescence in about 30% of the cases. Okay, so 1/3 of the cases, 2/3 of the cases, you just eject one of the black holes, or the system stays there and nothing much happens, etc. So we folded that in, we coupled that with a cosmological model for the evolution of the binary, of the massive black holes, and this shows you the merger rates of supermassive black hole binaries in the universe for two different models with light seeds and heavy seeds, where you have mergers because of dynamical friction and three-body scattering, etc. And when you just make the binary stall and you only rely, like by hand, we say every time you form a binary, it just stalls, and you just rely on the fact that the third black hole is coming in. So you see that, of course, the merger rate goes down. For example, if you take the high mass seed model, you have a total of 90 mergers per year. Okay, but even if you consider that all the binaries stall, you still end up with 40 mergers that are just triggered by these three-body interactions. Okay, so this is important because essentially, I hope, it reduces to virtually zero the chance of having zero detection of massive black hole mergers with LISA. Okay, so I think this is very important. Another important consequence of this is that what happens is that this chaotic three-body chaotic dynamics or secular dynamics excites the eccentricity of the inner binary to a ridiculous level. And what we are computing actually the eccentricity of these sources in the LISA band. And I don't see what is okay, this scale here, okay, this is 10 to the minus, this is 0. Okay, this is eccentricity of 1, 0.1, 0.01, 10 to the minus 3, 10 to the minus 4, okay? Or, well, you can see it here as well. So this is the eccentricity when a system enters in the LISA band, we start to build up SNR. We consider that a system is detectable at an SNR threshold of 8, okay? And we calculate what is the eccentricity there. And you see this distribution here. So you have a tail of objects that can enter the LISA band with eccentricity that is higher than 0.9, which is something that you don't do by any other means. In general, they can have some residual eccentricity in the LISA band. This system they evolve through standard channels, but they tend to be rather circular. So that's important for LISA because it guarantees a minimal merger rate. It gives the possibility of having extremely eccentric systems. And it's also important for pulsar timing. This is just to add to what Neil was saying yesterday. Because of course, if you merge 30% of the stalling binaries, right, you still build up a significant stochastic background of gravitational wave for the massive system. And what this plot is supposed to show is just, this is the gravitational wave background. You remember characteristic strain versus frequency. Neil showed a few plots like this yesterday. This is what you would have without triplets, right, with a single model. And this is what you get if you just stall all the binaries and you rely only on triplets. So, and this is the ratio between the two. So you see that you lose only between, a factor of 2 to 3 in signal in PTA, even if all binaries stall, okay? So that's very important for the future of pulsar timing astronomy as well. Yes? Yeah. Yes, actually, that's a very good point. When we did so in this code, we solved the three-body. They solved it. the three-body Hamiltonian. So we have all the terms of the PN expansion, like not only pairwise, just really from the three-body Hamiltonian. And we have the 1 PN, the 2 PN, and the 2.5 PN. And actually, one of the things that we found is that previous Newtonian simulation by, for example, Hoffman and Loeb and others, significantly overestimate the fraction of mergers at high mass ratio, at a small mass ratio, because exactly because of this, because they had only Newtonian dynamics, and what you find is that if you include relativistic precession, you actually suppress a significant fraction of mergers because you suppress the Kozai oscillations. Yeah, but this is accounted in these simulations. Yes. Well, we have an issue with waveform. You likely need, precessing spinning waveform for black holes with eccentricity of 0.95, and I don't think we have those now. I cannot even guarantee how relevant they are, right? It might be that mergers are extremely efficient, and you just form very few triplets. But it's a very interesting possibility. I mean, yes. I mean, I think 10, 15 years we should develop eccentric processing spinning waveform because they might be very relevant for LISA. Okay, so I'm running out of time. I started 5 minutes. So let me just, this was essentially the lecture, right? So we know that we have the supermassive black hole binaries with the merge, et cetera, et cetera. So why LISA is very important? And really, I just want to show one plot to close the lecture, which is the following, which I will get to that in a second. So this is just an example of a detection in LISA, right? This is even ELISA, I think, but so it's not optimal. What I want to just point out is that this looks like GW5914, right? With the difference that is not band pass filtered. GW5914 you see like that because you just clear out high and low frequency, otherwise you wouldn't see anything. This is the data stream from LISA, and this is emerging binary. Okay, supermassive black hole binary redshift 5. So you see by eye, you measure the properties of the system very accurately. And the only thing that I wanted to show you is this plot here. Okay, which is even, I should update this, is an old version. But this shows, again, it's cut here. So this is the logarithm of mass in solar masses. So this plot goes from 100 to 1 billion solar masses, okay? And this is redshift. So this is today, and this is redshift 20, so where we think, things start to become interesting, right? And these are contour of SNR for LISA detection of equal mass binary of this total mass at this redshift. So you see that if you have anything between, and actually this is an old plot for NGO. If you consider LISA, you should actually move this a factor of 3 to the left. So anything between few thousand solar masses to, tens of millions of solar masses merging anywhere in the universe is gonna be seen by LISA. Okay, this is everything merging anywhere in the universe. Okay, so that's why people get rather excited about that. So what I show here, just to give, so imagine, we detected gravitational waves. It was a great breakthrough. There was a Nobel Prize involved. We've seen the first electromagnetic counterparts start to do cosmology with gravitational waves. Amazing, right? What we've seen so far are 10 stellar mass objects at redshift lower than 0.1, so we are here. This is what we explored so far with gravitational waves, and that led to all this breakthrough. Just to give you an idea of the potential of LISA, this is what you're going to cover. Of course, LISA will happen together with, or maybe a little bit earlier, a little bit later, but together with third generation ground-based detectors, which are going to nicely cover this part of the parameter space up to very high redshift. so that you will have an almost complete coverage of the universe for, stellar mass object up to supermassive object, right? So this is the, I really think I just finished here. I mean, this is the key message that I wanted to tell you, is that, supermassive black hole are interesting tracer of galaxy formation, and they are tied to galaxy formation, etc. And they merge. We know that they merge. We hope that they merge. And any of these merger you're gonna see with LISA, okay? And the amount of science that you can do with this detection is, invaluable, and I would say largely unexplored. Because, for example, just imagine, I just want to leave you with this message. So imagine you detect 100 massive black hole binary mergers, for which you measure masses with sub-percent precision, you measure spins, you measure inclination at the spin, you measure the inclination of the spin of the merger, so you can actually fold all that in to work out what is the accretion history of supermassive black hole. You can work out, for example, how accretion proceeds, right? You can see if they are highly spinning, if they are low spinning, if the spins are aligned or not. And all of these are things that you cannot even dream of doing with any electromagnetic observation. Doesn't matter what your friend that is working on Athena Plus says, right? You will never get a clean measurements of the spin via electromagnetic measurements, because it's a mess. It's a messy process that involves a lot of physics that is poorly known, okay? But this is just general relativity. We understand it, well, maybe I don't, but people understand it rather well. And the simplicity of the model and that you use to work out these parameters is stunning compared to the models that you need to fit to get a spin out of a bloody X-ray spectrum, right? It's not. I love X-ray astronomy. I do a lot of work with X-ray astronomy and X-ray astronomers. But this is just to give you an idea of the potential of this mission. You will have clean measurements of black hole masses, black hole spin at all redshifts. And if there are primordial black holes of 1,000 solar masses at redshift 100, 1,000 no, but 10,000 solar masses at redshift 100, you see them with LISA, at redshift 100. So yeah, just to leave you excited for lunch. And yeah, I stop here. Right. Oh, the status of electromagnetic counterpart modeling is whatever. It's there. Okay. So there are several. Okay, one of the most interesting thing that you can do with supermassive black hole, of course, if you detect a counterpart, you do a lot of stuff, right? Because imagine that you have a supermassive black hole binary, okay? It merges, you measure the parameters very accurately, and then you see an electromagnetic counterpart, and you see the accretion happening on this system. So you're seeing the emission from, let's say, an accretion disk. So this offers you the possibility of studying the emission process and, of course, the accretion process onto a supermassive black hole of which you know the mass, the spin orientation, which is, something that is stunning, right? Because we just infer these properties from the spectra. So you can couple the spectra and all the information that you have from accretion with the exact information from the accreting object. So you can do, amazing accretion physics there. Of course, it's important also for cosmology, because if you get a counterpart, you get a redshift, etc. Now, unfortunately, I have to say that we don't know much about the emission of these objects, right? So there are models for in which you have periodic accretion related to the period of the binary. So if you have an spiraling binary and you have an accretion disk, the period of the binary is somewhat imprinted in the accretion of gas. And this is something that people are simulating with SPH and other techniques, MHD simulations. But you know, from accretion periodicity to periodicity in the light curve, you have to study all the radiation transfer, and that's not been done yet. So it's not clear whether these, you know, periodicities that you see in the accretion of the binary will translate into periodic features that you can use to see these, to identify these merging systems. Another thing is, of course, that you can, you know, there are other models. You can generate, for example, jets. If you have this binary in a magnetic field, the twisting of the magnetic field that generates jets that can extract energy from the black hole horizon via the Blansford-Nash effect. There were simulation by Palenzuela and other among these, and this can be a transient counterpart. But there have been other simulations. So there are, in this case, I have to say there have been simulations that found significant, you know, bursts, like this one or this one as well. But there have been other simulations that, you know, they find essentially not much. So you have these jets, etc. You merge the black hole. Yes, there is a bit of a reorientation of the jet, but it's hard to find a clear signature. So I would say really the modeling of the observation signature of supermassive black hole binaries and mergers, it's really in its infancy. So we really have, you know, we have like 15 years to come up with something a little bit more solid to use for, you know, detecting counterpart of these events. Yeah, sorry for the long answer, but really, you know, the short one is we don't know.
And it's hard to watch.
Yeah.